Section 3.10, Linear Approximations and Differentials. The approximation f of x is approximately f of a plus f prime of a times x minus a is called a linear approximation or tangent line approximation of f at a. The linear function whose graph is this tangent line, which we'll call L of x, is called the linearization of f at a. This should make sense as a definition because remember that we approximated the derivative using the slope of the secant line, f of x minus f of a over x minus a. So if we multiply both sides by x minus a, that moves this over here. So we get f prime of a times x minus a. And then if we just add f of a to both sides, we get f prime of a times x minus a plus f of a is approximately f of x. So let's use this to find the linearization of the function f of x equals square root of x plus 3. We'll do it at a equals 1 and use that to approximate numbers square root of 3.98 and square root of 4.05. The idea here is that it's usually easier to calculate a derivative and evaluate at some easy point, like at a equals 1. If we were to plug that in for x, we'd just be doing the square root of 4. And then taking that easy value of the function and the derivative, which will hopefully be easier, we can use that to approximate a complicated value of a function, like 3.98 or 4.05. So we're given that f of x is x plus 3 to the 1/2. That's square root of x plus 3. That means that the derivative can be taken using the chain rule. So we put the half out in front, keep our x plus 3, reduce this to minus 1/2. And that's the same as 1 over 2 rad x plus 3. Okay, so let's look at what our linearization function is. Remember we're doing this at a equals 1. So we're looking for f of 1 plus f prime of 1 times x minus 1. Okay, well, if we plug in 1 for f of x, like I said, 1 plus 3 is 4, square root of 4 is 2. And then we add that to 1/4 times x minus 1. Because plugging 1 over here gives you 1/4. Okay, so that ends up becoming 7 over 4 plus x over 4. So that means that we know that f of x, the square root of x plus 3, can be approximated by this linear function. And it already looks less complicated. Trying to do a square root in your head is typically harder than trying to do, a linear function evaluation. So it's kind of nice that we can use this linear function to approximate this square root, and in general we can use this linear function to approximate any crazy function, or almost any crazy function. So we want to do this for 3.98. So that's 7 over 4 plus 0.98 over 4, which is 1.995. If we want to do it for 4.05, that's 7 over 4 plus 1.05 over 4, which is 2.0125. If we were to graph this, so let's say here's minus, oops, actually I'll draw the thing first and cheat. So now I'll put minus 3 over there and put 1 over here. Okay, so then this is y equals square root of x plus 3. I'm looking at the point when a equals 1. So I'm looking for the tangent line approximation at 1. So we draw a nice tangent line, something like that. So that's what y equals 7 over 4 plus x over 4 is. Notice that if I'm really close to 1 for x, like I'm over here on this function, then I look at the tangent line approximation for that. That's this y value instead. Those y values are very close to each other. So it's a very good approximation if you're as close as like square root of 3.98 in this case, because 0.98 is very close to 1. Oh, actually, in this case, I'm on the right side of 1, so this is this one 1.05. 3.98 would be over here for 0.98 before the 1. And you can also see that if I were to go farther along, let's say over here, and I were to try to approximate with the y value over here, it keeps getting farther away. The tangent line becomes a poorer approximation the farther away you go from the point that you choose for a. Okay, we want to know if these approximations are overestimates or underestimates. Well, according to this, the tangent line is always above this curve. So we could say that they are overestimates. For what values of x is the linear approximation that we just calculated, square root of x plus 3 is approximately 7 over 4 plus x over 4, accurate to within 0.5? What about accuracy to within 0.1? If we want it to be accurate within 0.5, that's the same thing as saying that we want the difference between these guys to be smaller than 0.5. So we want that to be the difference, positive or negative, so we look at the absolute value, the distance between them. So we want this absolute value to be smaller than 0.5. So the difference in the y values should be smaller than 0.5. That makes our approximation accurate within 0.5. Well, we can get rid of the absolute value. So this is the same as minus 0.5 on the left and on the right. And absolute value, when you have a difference inside, it does not matter the order that you subtract them, because if you subtract in one order it's positive, in the other order it's negative, but then absolute value makes it positive. So I'm just going to swap the order. Okay, now I'll add square root of x plus 3 to all three sides in order to cancel it out in the middle. Let's use our handy-dandy calculator emulator. We want to put each of these sides of the inequality into different curves and graph them and see where the middle one will be stuck in between the other ones. So 7 over 4 plus x over 4, and then square root of x plus 3 minus 0.5 square root of x plus 3 plus 0.5. Okay, it looks like our blue curve is the one that we wanted to sandwich in between these guys. It's above the red curve, so that's good, and it's below the black curve sometimes, but it intersects on the left and right. So let's calculate those points of intersection. So that's my first curve. My second one will not be my red one. I want it to be the black one. And we'll guess that it's over here. Okay, so it looks like negative 2.66. So let's go a little bit farther. We can just say that it's negative 2.6 if we go a little bit to the right to be on the safe side. So let's do the other one now. Calculate intersection, first curve, second curve will be black, and we'll guess that it's over here this time. Okay, looks like about 8.66, so let's go a little bit smaller. Go backwards to be safe, so we'll say it's 8.6. So that means that this thing is accurate, this linearization, within 0.5 whenever x is between negative 2.6 and 8.6. Okay, we want to also do it for accuracy within 0.1, so we have the exact same thing to plot. We'll just change the minus 0.5 to minus 0.1. Okay, so we go back to our calculator. We'll change this to 0.1. Hit graph. It's a little bit harder to see now, but it's probably still above. Let's double check. Hit zoom. Yeah, so the blue curve is still above the red curve, but it crosses with the black curve. So it looks like we should be good over there. Let's zoom out. And let's calculate our intersection. First curve blue, second curve black. Guess over there. Looks like minus 1.13. So make it minus 1.1 to be safe. And this time we'll guess that it's over there. Alright, looks like 3.93 something. So we'll go smaller, make it 3.9, so that we're on the safe side. So this thing will be accurate within 0.1 when x is between minus 1.1 and 3.9. If y equals f of x, where f is a differentiable function, then the differential, dx, is an independent variable. That is, dx can be given the value of any real number. The differential dy is then defined in terms of dx by the equation dy equals f prime of x dx. This is kind of like when you had y equal, I don't know, if you have a linear function mx plus b, then x was the independent variable and y was the dependent variable. You can make x whatever you want, the y value would depend on it. Well, now we have a dx as our independent variable. You make dx anything, and then the y value, the dy value, depends on that dx value. So the way that we visualize this usually is by setting dx equal to delta x. Whatever our change in x is for our curve, we just let dx equal that because dx is an independent variable. We can let it equal anything. Then we look at dy compared to delta y. Remember that delta y is just the change in the y value of the curve. If we let dx equal delta x, then dy becomes the y value that shows the change for the tangent line. So the delta y value, that means, can be approximated using the dy value, which is usually going to be easier to calculate. just as before when we were trying to calculate tangent approximations for values of the function. So we can approximate values of the function using the linearization, and we can approximate values for our delta y, our change in y, using our differential dy. Let's compare the values of delta y and dy if y equals f of x equals x cubed plus x squared minus 2x plus 1, and x changes from 2 to 2.05. So we need to look at what f of 2 is. Well, that's 2 cubed plus 2 squared minus 2 times 2 plus 1, so it's 9. Then we need to look at f of 2.05. So that's 2.05 cubed plus 2.05 squared minus 2 times 2.05 plus 1. So that's 9.717625. Okay, the delta y, the change in y, is just the difference of these two y values. So f of 2.05 minus f of 2, which is 0.717625. If we want dy, by definition, that's f prime of x delta x. So that equals 3x squared plus 2x minus 2 when we take the derivative. And we want to know what it is in this case. So that's plugging in. We get 3 times 2 squared plus 2 times 2 minus 2 times 0.05, which is 0.7. So you can see these values are pretty close to each other. But you can also see that this was a lot more work to calculate than just this. Let's look from 2 to 2.01. So that's, again, f of 2.01. So we get 2.01 cubed plus 2.01 squared minus 2 times 2.01 plus 1, which is 9.140701. Delta y is the difference between f of 2.01 and f of 2. So that's 0.140701. Okay, dy, we already got the derivative, so we just plug in 3 times 2 squared plus 2 times 2 minus 2, but this time we multiply by 0.01 and we get 0.14. Now you could see that it's even a closer approximation for the change in y, because we're even closer to that point at which we're taking our tangent line. You can see that the closer you get, the smaller the difference between delta y and dy becomes. The radius of a sphere was measured and found to be 21 centimeters with a possible error measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? Well, if dr, the change in the the differential of the radius is equal to the change in the radius, which is in this case the error, right? Then delta v for volume will be approximately dv. In other words, our error in volume is approximately our volume differential. So again, what we're saying is that radius in this case is the independent variable. Volume depends on the radius, that's our dependent variable. So we look at the error in the radius, we set that equal to our radius differential, and then we say that that'll make our volume differential approximately equal to our error in volume. So let's calculate the volume differential. Whatever it is, it's got to be close to this error, so we won't even have to look at that. Okay, so remember that for volume of a sphere, it's 4/3 pi r cubed. So when you take 4/3 pi r cubed and you take the derivative, the 3 jumps out in front and cancels and just leaves you with 4 pi r squared. So we have 4 pi r squared dr when we're taking our differential. So that means that dv is equal to 4 pi times 21 squared times 0.05, which is approximately 277 cubic centimeters. So that's our error in volume, using that value of the radius. The maximum error, actually, is approximately 277. However, this doesn't really give you as good of a picture as, say, the relative error, which can be calculated by taking the error dividing by volume. So that means we can approximate it by taking the differential and dividing by volume. So that's 4 pi r squared dr divided by 4/3 pi r cubed, which leaves you with 3 dr over r. So that means that the error, the relative error for volume, is 3 times the relative error of the radius. So looking at this particular problem, it's 3 times 0.05 over 21, which is about 3 times 0.0024. So that equals 0.007. So that means that this 0.007 is the relative error in the volume. This 0.0024 was the relative error of the radius. So I should probably write in volume, or in calculated volume. This was the relative error in the calculated radius, or the measured radius. So we can also say that this is, we can express it as a percent to get the percent error. So this would be 0.7% for percent error, and this would be 0.24% for percent error for the radius. Compare that to this value, which was just the error in general.